All right, folks, these are what I call forced pivot problems. And let's compare that to a free pivot. So if you just, this is like throwing a wrench, bird's eye view. So the wrench is like rolling around on the floor and it's going to rotate, but they marked the center of mass of the wrench. And so it's going to rotate about the center of mass. Okay, that's a fact that you should know. We're not going to really use it until angular momentum, but just know that if you just threw something in the air, it will rotate about the center of mass, and the center of mass will travel as a particle. So in this case, a straight line. But I also stole this picture of somebody throwing like a mallet, and the center of mass of the mallet is moving in an arc. And all the little bits of mallet are rotating about the center of mass. Okay, so that's pretty complicated. So let's make things a little bit easier. We are going to force, if you nail something to the wall or make a hinge or whatever, you have forced the object to pivot about this point, which is not the center of mass. Okay, so that's what I mean by a forced pivot. You're forcing it by constraining it with some kind of solid axle to pivot about a specific location that is not a secret. You know, if it's not clear, just ask. Okay, so this is something that everybody needs to know. It does show up in the AP, but it also shows up on my test. I think it's an important trick. So you are given the formula for I for a meter stick or any rod, you know, anything that's solid, about the end is 1/3 ml squared. So when I passed around the meter sticks to everybody with all the stuff on it, just pretend like there was nothing else on it, and you were going to grab it about the end, not about the middle. So you're grabbing it about the end. That is given. That is a given formula. And I think it's important for you to know how to derive how that changes if you decide not to grab it at the 0 meter mark, but anywhere else. So the example problem is the pivot point is 1/3 of the way down this 2x4 that is of length, unknown length L. Okay, so that is the pivot. So this is the trick to find the rotational inertia about any point. You are going to treat that like a red meter stick, because the pivot point is now about the end of that red meter stick, plus a purple meter stick, not meter stick, sorry, purple 2x4. And so we're treating it as two separate objects. Each of those is pivoted about the end, right? Because now the pivot is at the end of the red shape and at the end of the purple shape. So I tote is going to be in this case, I'm going to call it, say, red instead of left, plus I purple. Okay, and each one of those is 1/3, however much mass we had, times however much length we have. Okay, and then how much mass is this? Well, it's 1/3 of the mass, right? That red amount is 1/3 of the total. And what is the length? Well, the length is also 1/3 of the total. And then, oops, that's a bad 3. If this is L over 3, this is 2/3 L. So I have 2/3 of the mass on the right side, and the length is also 2/3. Okay, so this is going to reduce to ML squared over 9 times 9, or 81. plus an ml squared. And then we got a 2 times 2 more 2, so that's an 8. 4 times 2, also over 9 times 9, or 81. Things are going to clean up a lot because 8 plus 1 is 9 ml squared over 81. And then 9 goes into 81 9 times. Okay, and then you could check your work if you wanted. You can see that that pivot point is closer to the center of mass than grabbing it at the end, and ml squared over 9 is less than ml squared over 3. Okay, so on the when you are tested on this, which in 2026 is different for each class, I will put that pivot point potentially anywhere, right? Like the pivot point could be a fourth of the way down or whatever, but you're just going to divide it into stuff on the left, stuff on the right of the pivot, and the total rotational inertia is just the sum of two different values. Okay, and then once you find I, then what's going to happen? Well, what's going to happen is the meter stick is going to rotate, right? Because there's more torque on this side, like this is heavier than that. So what I recommend that you do is draw the meter stick. This is point, again, it's not a meter stick, it's some arbitrary length, but you know what I mean. So this is point A, and that is point B. You have to decide on your sea level. And remember what's important for calculating MGH, because mass is changing height, is the height of the center of mass, which is at L over 2. So you can, I mean, I think there's two options. I don't know that one's better than the other. You could define the bottom of the meter stick here at sea level, or you could define this as sea level. If you define the initial location as sea level, then you're going to be below sea level at point B, because right, the center of mass is here. It doesn't matter. Actually, let's call this sea level, but you really need to pick and label on your diagram, or you're going to, you're likely to make a mistake. I'm not going to say you will, but it's tricky. Okay, so the meter stick goes from point A to point B. The center of mass travels in an arc, which means it is only rotating. It is not translating, right? Because we're not throwing this object through space. We've nailed it into place, so it can only rotate. Okay, and then the question is, I think this is an AP problem, but and I think the question is to find the speed at the end. I think that's the fundamental question, but let's find omega at point B. Okay, so again, mass is changing height, so we're going to say TME at location A plus work done, but we're neglecting any friction on the pivot, so we're saying there's no work done, equals TME at B. Okay, so at point A, it's always smart to potentially write all the terms and then make them 0, right? Better that than to forget about one term. Because on the recent pulley lab, I kept forgetting about the MGH for the object that was ascending. Okay, so at point A, is the center of mass above sea level? Absolutely. This is really tricky. Don't go on autopilot, be really careful. It is 2/3 L above sea level because we define sea level as the bottom of that meter stick. Okay, so we've got M times G, we're going to leave it as variables, times 2/3 L. It is not moving. We're releasing it from rest, and the torque of its own weight is going to make it rotate. But right now it's not rotating. It's not translating. Awesome. That'll give us more room. Okay, don't go on autopilot. This is not 0. For whatever reason, people tend to focus on the end of the meter stick and say that, it's at sea level. You care about the center of mass, and the center of mass is midway up the piece of, the meter stick. So this is mg L over 2 above sea level at point B. This is 0 because it is only rotating. It is not going through. So this is only a merry-go-round, not a merry-go-round and a cruise ship. Okay. So if this seems a little bit goofy to you, go back, and I made a play pause it where there was a bunch of different options for you to check your work to understand, when it had this term, when it has that term. But the trick is, the center of mass is traveling in a circle. So it is only rotating. If it were translating, it would be doing like that. It would be translating and rotating. Okay. So plus 1/2 I, which was ml squared over 9, times omega squared. And this is what we're looking for. We're looking for omega. All right, so one of the reasons the AP sometimes does things with variables is because it actually makes things easier, right? The M's cancel, 1L cancel, so be really careful. Just cancel 1 there. And then I'm going to do some, so we're going to have 2/3 G minus G over 2 equals L over 18 omega squared. Okay, so common denominator would be 6. So we have 6G minus 6G equals L over 18 omega squared. 4 minus 3 is 1, so we have G over 6. Okay, and then we have 18/6. This is a G. We have 18. We multiply both sides by 18, which gives us 3G divided both sides by L equals omega squared, solving for omega, and you get the square root of 3G over L. If you're like, I have no idea if that's right or not, we can at least check our units. G is in meters per second squared divided by L, which is in meters, which gives you the square root of the meters cancel, 1 over second squared, or 1 over second, which is great because omega is in radians per second, and a radian is dimensionless. Okay, so remember that number, square root of 3G over L. That is omega. Oh, okay, oops, label the center of mass. We already did that. And then again, this problem, it was really tricky because it asks you to find the linear speed of a point at the end of the rod, letting you maybe think that there's a 1/2 mv squared term. So they should have said, and again, I don't have the AP sheet with me because I'm trying to do this super quick for people who can't get in due to snow tomorrow. I stole this picture because they should have said tangential speed, because that point of the rod, if there was like a piece of mud on it, it's going to fly off tangent. It is only moving because it is on something that is rotating. It happens to be going through space. It's traveling through space in an arc, but if it couldn't hold on and flew off tangent, that is the speed they want you to solve. And so now we're in plug and chug land, because the tangential speed is proportional to how fast the record player is going and how far it is from the pivot, right? See, the farther you are from the pivot, the bigger these vectors are. Okay, so the tangential speed is super plug and chug. Let's do that over here. The speed at the end of the rod. I'm pretty sure that's the question. If it's not, then you will learn something by doing whatever it is. Omega is kind of a goofy square root, but so it's not super clean, but it's still, that's what it is, times R. Now be careful, R is not L. How far is this point away from the pivot? It is 2/3 of the way It's 2/3 L. Okay. Technically, that is the answer. When I was in college, this was not acceptable, because you've got an L in two spots. Okay, so I I will try to find out what the AP whether the AP cares or not, but this is really bad form, I think. So you want to bring this inside the square root. So to bring it inside the square root, you got to square it. So that's 4/9 L squared. And then you can see things are going to clean up. It just cleans things up a lot. One of these L's cancels. One of these 3's cancel. So what do we got? 4/3 GL. That is the tangential speed, because it would fly off tangent, of the very, very end of the meter stick. And that is what you're going to do in the lab, is you are going to predict the speed of the meter stick and then use a photo gate to confirm that you are correct. Okay, I think that might be it.